Hello everyone, Murad is here, and today we're going to try to tackle with the very last third assignment under the framework of database systems course. So without any further ado, let's get it started. Just one quick note is that before starting the recording, I made some preliminary research and wrote down my own document script, which we might be referring to in order to accelerate the process of completion the assignment. So let's come to the problem statement. Out of two given options, quite expectably, we will proceed with the second one, which is query optimization problem. So the completion of this task will be divided into four parts. So in the first part, let's call it pre-processing part. We will basically create our database, connect to it, establish these two tables. Then we will, using copy command, we will populate these two tables with the content of these txt files. Then we will run this generate user transaction SQL, which will generate the two empty tables, users and transactions, and give us the generate value procedure. And then we're going to run the generate value procedure, which in its own turn is going to populate those users and transactions tables with the random content that it generates based upon the content of the women names and men names tables. And it will also provide us with the query that we're going to have to optimize. After that, in part two, we will deeply analyze analyze a statement. We'll have some more in-depth insight into the way the query that we'll need to optimize is actually being processed by the database in the background, which alongside the knowledge of the role structure of the database itself will enable us to understand what are the problems, what are the reasons behind the slow performance of the proposed query. Basically, we will also answer this question in that part. Well, in part three, after having understood what is the problem behind the slow performance, we will try to propose and implement some optimization techniques, not limited to partitioning the tables, providing some indexes, using explicit joins, subqueries, maybe this sort of stuff. We'll see how it goes depending on our case. And finally, it's also important to mention that we will also be, as it's asked here, we will also be referring to a relational algebra diagram for it seems like here it's only asked for the relational algebra only for the initially proposed query, but if we need to, for the comparison purposes, we'll also generate the one for the optimized one. But we'll be the purpose of us referring to this relational algebra diagrams is basically it will give us, obviously, in order to be able to optimize a query, it's not enough to understand how the background process, how the database deals it, but it's also important to understand from our perspective how exactly the query is being processed, and these diagrams are going to help us out throughout the video. Well, that's basically it about the introduction. Now let's proceed with part one. So to do that, let's come to our beautiful shell. We're going to firstly we're going to create a database. Let's call it assignment 3. Yeah, I know it's quite an original name, but still, let's connect to it. Assignment 3. Okay, now by the way, it's also important to mention that for the purpose of this assignment, we're going to be using two tools, shell and sometimes pgadmin, since we're allowed to do that during the class. If you remember, you will see why precisely, because there are some cases when the shell goes crazy. For instance, when we'll try to populate the tables from the file, we will deal with some encoding problems there. To overcome which we're basically kind of going to use the pgadmin. So although it's obvious that both of them, all of the stuff that we're doing can be done from both shell and pgadmin, just for the ease of that, let's do it from here. So we have successfully created two tables. We can verify that. Let's refresh. There they are. Or if we wish, we can just say D to list all possible relations, and it's going to be main names. Okay, amazing. Now the next step we need to do, let's see, we need to populate those tables with the content of the txt file. To do that, we're going to use these two commands. Basically the copy command. Let's get rid of this little guy. Let's run it. Yep. So copy. In the first one, it copied 360 rows basically, and for the second copy, it copied 282. Well, we can quickly verify that. My names. So there they are, and the same should be for the other one. For instance, if we add just v women, yeah, we get the very same thing. So the problem was here with the encoding. So for instance, if we try to run the very same command from here to view the content of the table, populated one, if we say human names, we will see that there are some problems with basically with encoding stuff. So okay, irrespective of however much we try to handle that, by ensuring that both the encoding of the DBMS and the text files that we use for the population are the same. We tried all of the possible encodings from Postgres documentation, but none of them worked out. Therefore, we asked for permission to use other tools, and gladly we got that permission. So, okay, now we'll need to generate user transaction SQL. For that, let's come here. Let's come here. Let's Control C, come back, and F5. Yep. So basically what this PLSQL script did, it should have created simply two tables. Yeah, transactions and user list. These two are empty for now, but what is more important, that it's created a stored procedure. Let's generate values. Yeah, there it is. And this generate procedure, when we call it right now, stored procedure, when we call it right now, what it will do, it will use the content of men names and women names txt, like tables, to randomly generate some stuff to populate these transactions and user list table with, and at the end it should provide us with a random query that we're going to have to optimize. So let's run it. It's generate values. Let's try again. So yeah, it has started to run successfully. It will take quite a while, so not to lose our time, I'll be right back once the process of execution is done. So here I am, alongside with our procedure having executed successfully and returned this query for us to analyze. From this point, we'll proceed with part 2, where we'll basically analyze our database together with the initial query planning as discussed in the introduction part, to understand what precisely causes, given the circumstances, the database and the query, what exactly causes the delay, the slow performance behind this query that we're going to optimize. Okay, let's continue with part 2, which is the database and initial query planning exploration. So let's come here. We will start off with analyzing the relational algebra diagram for our query, for the purpose query that we will need to optimize. Because in order to optimize it, first of all, we need to understand in which order exactly the execution is getting done. So let's start from the bottom, because that is the order. That's how the order goes. So first of all, we can see here the cross-join operator. So first of all, even in our query, if we take a look, the first thing that will happen, it will cross-join user list and transactions. It will cross-join these two tables. Then based on the given predicate, it will apply the selection conditional operator sigma to filter out the resulting set, which we got as a result of this Cartesian product, based on the following predicate, which we can view in our query here, where to edit this little guy here. After that, we will get to the gamma operator, which basically stands for the aggregation or grouping by. This is the part that is given in grouping by and aggregation that is used there. After that, the resulting set of this gamma operation will be filtered out by sigma selection conditional operator once again, based on this condition of counting amount must be greater than 5. That's basically the having part of filtering out the resulting set after grouping by. Then after that comes the select part, the projection operator, which basically selects which transaction, in which form we would like to receive a form, like taking which fields, which columns, in which order, giving aliases. For instance, like here, it is the alias for the sum amount, and by the way, these below are the alias U is for user list, T for transaction. And finally, as expected, the ordering is done. This arrow here, it indicates that it's done based on empty sum, based on empty sum in descending, decreasing order. So how do we know whether this relational algebra diagram is correct? Well, it's just enough for us to ensure that it coincides with the well-known execution order of different commands in Postgres. And if we check that, we'll see that it indeed coincides with that. So now that we are done with the relational algebra diagram, the next thing we'll do, we'll come to pgadmin, and we'll try to explore the content of the newly generated tables, transactions, select everything in transactions. It will take, well, actually, we don't need to go there. We already know what kind of fields are there. Instead, what is more important than that is to understand the scale of the database that we are dealing with. So let's run the query and wait for a little bit until it's getting executed. Okay, we have about 1 million tuples transactions in transactional table, and if we check the same for user release table, which these transactions are associated with, let's see how many people have there. 1 million. So we have 1 million people, which correspond to 100 million transactions. The main takeaway from here for us, for now, is that we're dealing with quite a large data set. Now let's continue with the analyzing the initial query execution plan. To do so, we're going to take our initial query, which was proposed to us, which is this one, and simply add the explain analyze statement to it. Let's let it run, and then we'll try to analyze everything one by one, which will enable us to understand the current state of things in a much better manner. So this is our data output. Let's go line by line. So first of all comes the limit, which basically the first line implies that the query is simply limited to 10 results. That's what we have in our query, to 10 results as per our SQL command. Basically, the cost here indicates this amount, right? And total cost is still this amount. This estimated, this is the total cost, pretty much coincided with each other. And this is the actual time that was needed in order to retrieve, again, estimated time and the actual time needed to retrieve exactly 10 rows from the resulting set. Next comes the sorting part. Again, here we have the estimated cost and the actual cost, the estimated time and the actual time. So we know the sort key here tells us how exactly, based on which key it was sorted. We know that it was sorted based on the sum transaction amount in descending order, just as specified here. And the sort method it uses is the quicksort, which is one of the most typical sort algorithms that databases use for such purposes. Next comes the group aggregate part. So that is exactly the part where the group by statement lies within and having both of them. So the database is grouping by user ID, fname, last name, and filtering this row. This is the having part, filtering these rows based on this having count the amount greater than 5 condition. So only those transactions, only those groups which have more than 5 transactions, right? So the gather merge part, basically this operation is related to the parallel processing in Postgres. This particular line more precisely to the Postgres query planner. So remember the intra-query stuff, executing some parts of the same query in parallel. So for that, we know that what Postgres does, it allocates some sort of workers. So it expected to allocate exactly 2 workers for the purposes of running this, executing the query in parallel, and at the end it still launched both of them. So next we have the sort part, and gather merge. Basically, after these workers are done, this is the amount needed for the Postgres query planner in order to retrieve the work they've done and combine together and basically proceed any further. So next, we have, that's exactly some other detailed information about the same process. Next, we have parallel hash join. So basically, the database performs a hash join operation to match rows from user ID, from user list and transaction tables between the ID match. That's basically the join part of a Cartesian product part. The operation is done in parallel to speed up the process, and the hash condition indicate that the condition used for the join. This is basically the condition of our join. Next off comes the parallel sequential scan part, the database, which basically implies that currently the database scanning the user list and transactions tables in parallel. So for user list, for the user list table, it's filtering the rows the schools in SPIA based on this predicate. And for the transactions table, it's also filtering it based on the following predicate. And we see for hashing have buckets that it uses for the purpose of hashing. This is at the very bottom here we have the planning time, and finally the execution time, the actual execution time. Next on, let's try to answer the question that was asked. So basically, how the cost is going to get changed if we remove one of the predicates. So the general tendency states that if the predicate we are removing there is itself removing a significant number of rows from consideration. That is, if in our database there are many rows in the transaction table that don't actually meet the condition of TR date, this one, then removing this predicate could actually increase the cost. And it makes sense. This is because the database would need to process more rows during the join and group by operations. It could also increase the amount of data that needs to be stored, which could increase the cost of the sort operation. Given that the amount of rows that were removed from the consideration is quite significant, we have about 34 million rows out of 100, remember, which got removed. We should expect that if we remove one of the predicates, the actual cost should go up. Let's actually try to do that. Let's remove one of the predicates, for instance this one, and try to run the very same query. It's 1,300,000 for now. And you see, not significantly, but we still can see that the cost actually increased. Okay, so which actually met our expectations. Now that we have talked about the relational algebra diagram for our query, as well as analyzed the queue execution plan in details, we can now state the problems that come up as a result of our analysis and the ways and propose the ways for us to solve them. So the first problem is the fact that we're dealing with quite a large data set, because as we saw, we have a very large number of records in transaction tables. That was about 100 million. This makes any operation on this table potentially slow, especially if the operations involve sorting or grouping, just like in our case. Next, we have sequential scans here. In our execution plan, as we saw, there are several sequential scans happening on both the transactions and user release tables. Sequential scans, they're slow because they read every single row in a table. Next comes joining large tables. Our query is joining the user release and transactions tables, and and the way it does that, it uses the Cartesian or product or the cross join by default, which basically means that all possible combinations of tuples must be processed. And it's obvious that some sort of redundancy there, and this sort of operation requires quite a lot of time, and the cost comes from with that as well. And the final problem that we need to address is filtering and aggregation. So basically, our query is also doing some heavy lifting stuff in terms of filtering data, as we could see, with the where clause, grouping the data with the group by clause, and then filtering again with the having clause. This operation that requires sorting and potentially creating temporary data structures, which can work really slow on large sets. So, okay, now that we know the problems that we have, let's talk about the ways we're going to address them. So the first thing we will do, in order to solve the problem with a large data set, we'll apply something called partitioning. Partitioning is basically a technique used to divide large tables into smaller ones, more manageable pieces called partitions. Each partition is basically just a subset of the data that can be operated on independently. In our case, partitioning the transactions table can be beneficial because first we have a large data set, and that's exactly the case when partitioning comes in handy, because when query is executing, it will no longer need to go through unneeded. It will no longer need to analyze scan unneeded tuples. It will only go and scan the partition that it needs to successfully execute itself. And given that we have such a great candidate for partition key, which is the TR date, a field in our transaction, and the overall situation, that is the way we're going to solve the problem with large data set. The problem with joins, the way we're going to address that, just as I said, the cross product, this Cartesian product, this cross join is quite slow because of its nature. So instead, we'll try to use inner join so that it will only take those tuples from both tables that share that meet the given predicate for the given fields. The problem next comes the problem with filtering and aggregation. This one we're going to address using indexing. Indexes are database structures that can dramatically speed up data retrieval. So, and the justification why we're going to use it here, just to solve the problem with filtering and aggregation. So first, we're performing a join on the user ID and field, and to join the user release and the transactions tables. So, and creating an index on both tables, it can drastically accelerate the process. We also have some filtering conditions. So our query includes where and having clauses, and indexes on the stuff they're working with, that is on TR date, skill, and amount, can also speed up the process. And once again, the problem with large data sets, as mentioned earlier, since we're working with a large data set, while indexes do come with some overhead, I mean, they need to be maintained during insertions, deletions, and updates. We're aware of that. We discussed it. The benefits in terms of faster data retrieval often outweigh the cost for large data sets. So basically, given that we're more interested in fast retrieval optimization stuff, indexes is quite a good choice to solve the problem with the filtering and aggregation. While it's obvious that it will slow down some other write operations for our database. So there are also, it's important to mention that there are also other ways of optimization, such as using materialized views, subqueries, and even dealing with parallelization stuff like these intra-queries. We can manually enforce the Postgres query planner to work the way we want it to, for instance, by playing around with the maximum number of workers or maximum number of workers per gather parameters. All of these methods can also accelerate the process depending on our needs in the database. Since we have limited time, we're not going to go into all of those. We'll just go into the one that we have already discussed. Next, start off with the implementation part. So the first thing we'll do, we'll try to apply some partitioning. For that, let's first create the partitioning table. Transactions, partition, Okay, we're gonna open it up like that. Come here. So transaction ID, which is serial. We're gonna set up a not null constraint on it, comma. We'll press it with tr date, which is supposed to be just a timestamp. Okay, not null constraint, user ID. Well, we're gonna put it integer just like it was in the original table. And finally, no, we still have amount numeric for 2 and terminal ID, which is going to be integer. Okay. Now we're gonna say partition by range. The partitioning key is going to be tr date from the predicate. Okay. Now we need to now that we've created the table, the partition table, we're gonna create individual partitions. The way we can do that, create table 10 partition of transactions partitioned for values from. Now we need to specify 2 timestamps. 2. Okay, so we'll start from 2010 January and finish off with 2011 January. Okay, added the first one, but we need to create the appropriate and corresponding partitions for each possible years so that the database could actually allocate the content of the original transactions table into these partitions. Therefore, we're going to repeat this one multiple times. Oops. Like this, like this, like this. Here, we're gonna say 211, 212, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, and let's say 24, just in case as well. So we're gonna put 7 here, we're gonna put 8 here, we're gonna put 9 here, 20, 21, 22, 23, and finally 24. Let's adjust these values accordingly. 11, 12, 12, 13, 13, 14, finally 24, 25. Okay, now that we have created the partitions based upon them, we need to migrate all data to the new partition table. The way we're going to do that, we're going to say insert into transactions partitioned, select everything from transactions. Let's try to execute it. What happened? Syntax error. Oh, obviously we need to close them down. This. Yeah, it's obvious. They should be closed down differently. So here we are, everything is fixed. Let's give it some time to get executed. We'll be right back when the transitioning is done for our table. So now let's try to execute our optimized query. Basically the initial one, they only changed it that now we're using the partition table and inner join instead of the, I can even specify it this way, although they are going to be the same. Let's do it like even more explicit. And now let's run it and see whether the time has increased. Yeah, like the cost decreased. Yeah, as we can see, the initial cost was about 1,300,000, but now after applying partitioning, we're dealing with just 118,000. It's good, but it's still not enough. Therefore, the next step we're going to add, as mentioned in the previous part, we're going to add some indexes in order to deal with grouping by, aggregation, and filtering stuff. For this purpose, let's create those indexes. We're gonna say create index on user list ID on user list ID basically. Let me copy paste this, not to repeat myself 700 times. Okay. The second index we're going to create the ID transaction user ID, IDX transaction IDX transaction user ID on transaction on the partition table, transactions, here also transactions on transactions partition table, and it's going to be user ID, right? The next index is going to be ID user list school. Here we're gonna add a partial index as well, exactly for meeting up the particular predicate of this query. So it's gonna be on user list once again, and it's gonna be on user list school. And since it's a partial index, we need to specify the condition where school is SPIA. So the fourth one is going to be the index transactions user user ID tr date, user ID tr date, basically for the purposes of the join now. So on transactions partitioned, obviously transactions partitioned. And it's going to be a multi-column index, user ID and tier date, so that whenever these two guys need to be looked up in a pair, it will help us a lot. For instance, for the particular case of this query. Okay, that should be it. Let's try to execute it. We'll give some time for it to be executed, and once the indexes are created, we'll be right back. Okay, now that the indices are established, we're going to try to check the estimation cost now. For that, we'll use the query which is similar to the initial one. The only difference is that now we're going to be joining the transactions partition table that we just created, and we're going to use inner join instead of cross join for the purposes, for the reasons that we already discussed. Let's start to run it now. So we've got 97,000. It's still better. The performance improved using partitioning, but it's still not good enough. And as I stated, we're going to try multiple approaches. Therefore, we have an alternative to this one. Let's go with method 2. Instead of using partitioning, we will simply create a couple of indices and see how it goes. Again, similarly, the indices will be on the attributes used in the grouping by, aggregation, and filtering. Okay, index on transactions user ID. This is the first index. Let's copy paste it. 2, 3, I'm going to create 3 of them. The next one is going to be transactions tier date index, which is going to be on transactions tier date column. Is going to be a partial index. We're not using the index on the whole table because partial ones, they usually demonstrate a better performance. And since we are trying to optimize precisely this query, we're going to go with a partial one. So we're going to filter it out and say where tier date is actually the one we're looking for. So 200. Okay. 0102. And finally, the third index we're going to create is user list school. User list school. A user list school registered index. User on user list, it's going to be on the user list table. So user list and school registered. School registered. As you can see, this is a multi-column index, so that whenever these two attributes are looked up together, the process will be accelerated. Okay, let's try to run it. And we'll be right back once the indexes are created. So here we are, the indexes have successfully been created. The next step we'll proceed with, we'll simply run the initial having command that we had this way. Once again, the only thing we changed here is just use to the inner join instead of the cross join. So let's see whether this will help us to improve our performance. It's supposed to. So as we can see, the performance improved drastically. Now it shows just the cost is indicated to be just 17, and at the beginning it was 1 million or something. So actually, before we finalize, let's also try to experimentize with materialized views, because some sources they state that materialized views can accelerate the process of execution of a query, because we just need to execute them once and then we can use it however many times you want. So let's try to verify that. For that reason, we'll try to create a materialized view. Create materialized view. We're gonna call it user transactions as we're gonna say select basically whatever we had in the initial query, user ID, f name, l name, sum amount, its alias, which is empty sum. Then we have from user list, we're gonna call it u, join transactions, on, we're gonna say uid, uid equals t user ID, right? Then basically predicate, which was mtr date equals to actual date of our query, which was to like that. Okay, and the second predicate, the school, was supposed to be SPIA. And group by user ID, F name, basically just whatever we had in the initial query, L name, and let's not forget about having something out at the end based on the counting. So count greater than 5. So basically we're going to try to create this materialized new view now in order to accelerate the joining process. Okay, so let's try to execute it. And now we forgot to give an ls here. Should be like this. First name, last name. It should be like that. Okay, it was returned successfully. Now we're going to use this materialized view. Once again, we're going to use it to accelerate the joining and grouping by processes. So basically all the stuff besides sorting is going to be here, and in the original query the way we're going to execute it is going to be as follows. So since both grouping, aggregation, and joining are done within the materialized view, so we just compute that once, and after that we can use it in our initial query, and this very fact should also accelerate the process. Let's see whether it actually does so. Well, as we can see, the current execution cost, it became a little bit larger if compared to just the approach of simply using the indices on the table. So it was 16, about 17 for the previous one, and now it's about 24. So it increased a little bit. So the final verdict we're going to make is that using three approach, partitioning and indexes, it demonstrated the worst results for our particular case. The second place is going to be taken by the materialized view, and the very first place with the result of 24. The third place demonstrated the result of about 90,000, if I'm not mistaken. And the very first place, which is just the direct indexing approach, demonstrated the best results, about 17 units of cost. It's important to mention that when optimizing databases, there are several trade-offs we should keep in mind. So the first one is memory usage. Indexes and partition, they can consume a significant amount of memory. It's a well-known fact. Each additional index or partition will require more memory to store and manage. This may lead to increased costs if you're using a hosted database solution where you pay for storage. So the second one is the related one, the disk space. Indices, especially when created on large tables like ours, can consume a significant amount of disk space. This is another factor that could significantly potentially increase the cost. In sorting, it's also important to mention that we know indices, while their main advantage, and by the way, just to mention the types of indices, we didn't specify them externally, but when we don't specify any sort of index type, then by default Postgres creates a default B plus tree for us. So the third one is, while we know the main advantage of the indexes being the fact that they can accelerate drastically the process of returning the data, that is the select operations, that's basically the advantage that we use here. We should also keep in mind that besides the fact that they require quite a significant amount of memory, they also may quite significantly, considerably reduce the speed and the performance of write operations. I mean, insert, update, delete, this sort of operations. The next one is maintenance overhead. Partitioning and indexing, they add, in real life environment, they add obviously complexity to the database, which will require additional administrative work to be done. So for instance, while partitioning, you need to decide on a partition key and manage the creation of new partitions as the data grows. And the query performance, the final one, which basically we know that not all queries will benefit from array optimization. What we try to do in this video, in this tutorial, in this assignment, we just try to optimize the particular query that was given to us. But obviously, depending on the keyword, depending on the type of the database we're dealing with, whether it's uh, more heavily based or reading based, the approach that we're using, they will differ among the one that we listed throughout the video and applied. So for instance, a query that scans the entire table might not benefit from an index, or might even be slower due to the overhead of managing the index, right? So therefore, it's crucial to understand what kind of environments we're dealing with and to have an individual approach depending on the usage cases and needs of our database in real life. So just to finalize the recap, to recap the video, um, we started with the pre-processing the data. We prepared the floor for basically optimizing this stuff. Then in the second part, we discussed the relational algebra diagram for our initial query to have to get some better insights as to the way it performs. We also analyzed in detail the initial execution query plan to understand, alongside with the database structure, what were the reasons behind the slow performance of the particular query provided to us. After that, basically, after establishing the reasons for the slow performance, we also discussed some possible ways of optimizing those that we can use to optimize the performance. And then in part 3, we basically tried applying three ways, because as I said, it's impossible to wrap up all of them in just one video, encompass them all. So in this video, 3 methods were applied. The result they demonstrated, the partitioning showed the worst result, 100, I believe it was about 90,000. The second case took this materialized view with a cost of 24, and the first place is given just to the direct approach of indexing with a cost of about 17. And now let's actually calculate what is our improvement factor. The initial cost was about 1,284,000, and the final cost we could get was about, let's round it up, 70. So the final result we could get in this video, we could optimize the initial query by the factor of 75,500, which is quite a huge improvement. That's all for today. Thanks for your attention, and see you.